Okay, so today we are going to discuss on new type of new chapter here on friction. So basically, many of what we have discussed so far in the biomechanics mechanism or phenomena, we assume that there are no friction. We always assume, for example, in the pulley where the uh, rope is being attached to to the pulley. Yeah, we assume that there is no friction, so that then the rope can slide easily in on the surface of the pulley. However, if um, in ideal case it should be like that, but in reality that is not the case. In reality, when surface and surface interact with each other, there are what we call as friction. So when uh, the there will be a retarding force, yeah, a decelerating force opposite to the direction of the motion. So this is something which please you need to take into note, that the direction of the friction force is always opposite to the direction of the motion. Okay, not the resultant, not the other, the motion where the object move. When there is a surface interacting with that object, then there will be an opposite force opposing the motion direction. There are two types of friction, namely the dry friction and the fluid friction. The dry friction occurs when there are no liquid in between the two surfaces. But when there is liquid, small liquid, then fluid friction will happen. So again, friction force is always against the motion. Yeah, the direction is always against a motion. So for example, here, when we have an object being pushed with a force P to the right, then there will be a friction force opposing to this motion that is directed to the left, opposite to the direction of this P. And this F is called as the friction force. And the direction of the friction is always tangent to the surface, not making any angle, or not even, not alone perpendicular to the surface, but always tangent to the surface. It means parallel to the surface at the surface itself. Okay, then let's clean this. Okay, so this is the relationship between friction force F and the applied force P. So there are two types of friction force, which of course I believe you have learned this in high school physics. So first is what we call as the static friction force, yeah, this left part, and then the kinetic friction force Fk. The static friction force is dependent on the force applied to that object. So the static friction force occurs just before the object starts to move. So whenever we increase the force towards an object, then uh, there will be an opposing friction force at the surface, tangent to the surface, that is opposite to the direction of that pushing force. And whenever this pushing force does not exceed certain limit, then that friction force will always be in equilibrium with that pushing force. As a result, that object will not move, so it will stay at its place. However, when we push further, push further, we increase the pushing force to the object until some limit here, then the object will eventually move, okay, to the direction of its pushing force, and then uh, the friction force will be replaced with kinetic friction force Fk, whose value is constant towards the motion of that object. Okay, so this is the difference. In static friction force, they are always varying. The value is varying dependent on the value, depending on the value of the opposing force, the force that is pushed toward, or exerted toward the object to move that object. Until certain point, it's always in equilibrium. When that pushing force is above a certain threshold, then it will start to move. After that, then it will be replaced with that kinetic friction force, which is always constant and in opposite direction of the motion direction. The threshold we call is as the maximum static friction force, or Fm. The value of Fm equals to mu s times n. What is mu s? Mu s is the coefficient of static friction, and when it moves already, then the opposing friction force, the kinetic friction force, is called as Fk. Yeah, and Fk equals to the mu k times n, where mu k is the coefficient of kinetic friction. And both or the friction force Fs or Fm and Fk dependent is proportional to the value of n. What is n? N is the normal force. Normal force is the reaction force when an object is interacting with a surface. Okay, so at this left part, it is always in equilibrium. So the motion, the object does not move, and after a certain threshold, it will move. It will be in motion. So as we can see here from this graph, that friction force is a non-linear phenomenon, because after a certain while there is this what do you call it? It is being discontinued and then move again with certain constant value of Fk. The values of mu s depends on what surfaces interact with what surface. Yeah? So metal on metal has interaction has a mu s of 0.15 until 0.60. This again depends also on the characteristic of the surface, the morphology of the surface, the roughness of the surface, how rough is the surface, how smooth is the surface. Metal on wood can be a little bit larger because wood itself already has some roughness, so 0.2 to 0.6. Metal on rock is even larger, 0.3 to 0.7. Metal on leather, 0.3 to 0.6, etc. And here we have rubber on concrete, which has very large mu s, 0.6 until 0.90, because rubber itself we know is very sticky, has some stickiness, and when it is concrete itself is very rough. When the two interact with each other, they are very difficult to move against each other. So friction angle phi is the angle between the normal force and the resultant R between that normal force and the friction. Okay, so when we push an object with force P, for example, the object itself has a weight of mg. Okay, then a normal force will act on the object at the surface, usually equals to mg, because this is reaction force from the surface. Okay, then there will occur a friction force F, can be calculated from, if it is still in equilibrium, means F equals to mu s times n, the normal force, to the left, yeah, opposite to this pushing force. So then the resultant of F and N, yeah, is this force R, yeah, the resultant between these two. The angle, yeah, between the normal force and this resultant R, or phi, is what we call as the friction angle. So the friction angle equals, from this correlation, equals to, if we look here, so basically this is the F, yeah, the friction force, yeah, arc tangen phi equals to this F, yeah, divided by x is n. Okay, while F equals to mu s times n divided by n. Okay, so tangen phi equals to mu s, or phi equals to arctangen of mu. Okay, so this is the formula of phi, the angle, the friction angle. So mu s equals to tangent phi. So when we are given a problem in friction, about friction, the first is, as usual, we have to draw the free body diagram and then make sure that the friction force is directed against that direction of the motion. Yeah, always opposite to the direction of the motion. When there are cases involving two bodies or more, we have to draw the free body diagram similar to when we do deal with frames and machine problem. Remember in the previous chapter. So let's give some example. And depending on the types of problem, there are 5 categories of problem. Later we will see one by one. The first category is when all external forces and both coefficient of friction, μs and μk, are known. So we are asked to determine if the system is in equilibrium. Equilibrium means it is still static, does not move, or already in motion, starts to move. For example here, determine whether the block here is in equilibrium or in motion. Hence, find the magnitude and the direction of the friction force. So you are asked to find the direction of the friction force and also to determine if it is already starts to move or not. So remember, it will start to move when the friction force already above the friction maximum, yeah? the maximum static friction, Fm. It will be in equilibrium when the friction force is still below that threshold. Μs is known to be 0.3, μk is known to be 0.2, and here there are vertical force pointing downward, 500 Newton. Okay. The mass is not known, let's say here. Then there is a pushing force to the right equals to 100 Newton, and that block itself is located in a slope of 30 degrees from the horizontal line. So we have to first draw the free body diagram. Usually if we have slope, then the xy axis will be drawn with x tangent, yeah, to the slope and y vertical to the slope. Okay, so here we have vertically downward 500 Newton. We draw here like this, 100 Newton to the right, and then the normal force is always perpendicular to the surface. Now be careful here that the normal force is not like this. Yeah, so the normal force is not like this. Nope, but it is always this direction. Yeah? Because perpendicular to the surface, there is a surface here that the block is located on. So the normal force is always perpendicular to that surface, and the surface created the degree, yeah, because the slope here is 30 degree. The slope is 30 degree from the horizontal, and since this is 90 degree, okay, so this is 90 degree minus 30 degree or 60 degree, and then between this and this is 90 degree also. So this angle becomes 90 degree minus 60 degree equals to 30 degree. Okay, I hope this is quite clear. Okay, so here sigma fx equals 0. Yeah, fx is parallel to the slope. Yeah, then we calculate 100. So 100 cosine 30. How come? Let's try to. So we have to find here if the component of this 100 Newton is here plus this one, yeah, this value, this value. So this one is how much? This angle is 30 degree as well. Yeah? This is 30 degree. How come? So if we extend this further, because this is 30 degree, so this angle is 30 degree. That is why the x component of this 100 Newton, yeah, this value is 100 Newton cosine, okay, 30 degree. And this one, this value, the y component is 100 Newton sine 30 degree, but with negative value because it is downward towards the slope, towards the surface, the slope surface. Okay, Understand? So from here, sigma fx equals to 0, 100 cosine 30 degree plus f here is the friction force. Yeah. Okay, so here we assume here that the block is going to go down. So that is why we assume here that the force, the friction force goes to the right. Negative 500 Newton sine 30 degree. The fx, how come? So let's draw again. This is the 500 Newton. So if we draw into the xy direction, it will become this, yeah, this and this. So and this angle is 30 degree as well, right? This is 30 degree. This angle, yeah, the same as this angle. So the y component of this 500 Newton is 500 Newton cosine 30 degree, and the x component here is negative 500 Newton sine 30 degree, because it is above this angle. Sorry, in front of that angle. Okay. So from here, for category 1, the friction force is represented by F, not by mu s n. So in this case, F is assumed up the incline, meaning so the block is assumed to move or tend to move down the incline. And that's why plus F 100 cosine 30 degree plus F negative 500 sine 30 degree equals to 0. And here we obtain F equals to 163.4 Newton. So now there are two possibilities. If the answer is positive, means our assumed direction that the block is moving downward is correct. So when block is moving downward, it means that the friction is going upward. So then this is positive, so it means it is correct. But if we had instead negative answer, then the assumed direction of F will be incorrect. So it will be reverse direction of the F. So in this question, F is directed up the incline, and the block is moving or tend to move down the incline. So then we further calculate sigma Fy equals 0, n is perpendicular to the surface. It means according to the y-axis, negative 100 sine 30 degree. Yeah, this part. So let's draw again. The y component is this part. Yeah, this is 30 degree. So that's why this is 100 sine 30 degree. 100 sine 30 degree. Okay, minus 100 sine 30 degree. Minus 500 cosine 30 degree. So as we have explained earlier, this is the y component here. This is 30 degree. So this is minus 500 Newton cosine 30 degree. Okay, yeah. So I hope this is clear. Then I clear the drawing. So from here we obtain n equals to 483 Newton. Then we compare the magnitude of F with the magnitude of the maximum static friction force Fm. There are two possibilities. If F is larger than Fm, so here F is 160.4 Newton. Then the block is moving. If F is larger than Fm, then we know that the block is moving down the incline. Hence that Fk, we have to calculate then the kinetic friction force, because the friction force already changed from static into kinetic friction force. Yeah, Fk equals to mu k times n. When Fm, the maximum friction force, is larger than F, the opposite one, then we know that the block is still in equilibrium. The block tends to move down the incline, but it is still in equilibrium. It's not moving yet. Hence, the F, the actual F, the static friction force, will be equal to the calculated F here. Okay, the calculated F here, 163.4 Newton. So see here, our value is 163.4 Newton. Yeah, our calculated F from this free body diagram. Then we calculated Fm, the maximum static friction force is 0.3 times 483, the normal force, the mu s is, where is it? Mu s is 0.3, right? 0.3 times the normal force, 483, we obtain Fm equals to 144.9 Newton. So our value 163.4 Newton is larger than this Fm, larger than the maximum static friction force. What does it mean? It means that the force, friction force is already larger than Fm. It is already moving. It's not in equilibrium anymore. The block is already moving. So we have to calculate the kinetic friction force, the real. So the kinetic friction force has to be calculated from Fk. Fk equals to mu k, the kinetic friction coefficient times the normal force, okay, which is 0.2. Yeah, here, okay, 0.2 times 483, 483, yeah, which is 96.6 Newton. So this is the actual friction force, not the previously calculated 163.4 Newton. So be careful. Yeah? This is friction is non-linear problem. So that's why you have to investigate the case. So notes to be paid attention here is that we have to choose a suitable pair of axes, then reverse the direction of F, the friction force, if the answer of the first part is negative. If the answer here is negative, not positive like this, but negative, then we know that the friction force would be the other way around. Okay, in category 2, the block is on the verge of moving. So the system is in equilibrium. It is just about to move. So the coefficient of static friction is known. Yeah. Determine the required quantity P such that it will start to move. Example here, determine the range of P so that the system is in equilibrium. Example here, we have the block is on the slope of having a 25-degree angle to the horizontal line. Then the force is applied, a force is applied with 45 degree towards the horizontal line. Okay, P here. Mu S is 0.2 per 100 Newton is force is applied downward to the mass vertically downward per 100 Newton. Now, what is the value of P? So that the system is in equilibrium. It means that the friction has to be lower than or equal to the Fm, the maximum static friction force, if mu s is known 0.2. So there are two possibilities. The block is on the verge of moving down the incline downward. Yeah, in this case, then the friction force will be directed upward. Alternatively, it may also be on the verge of moving upward, right? Because of the force P here. So the friction force means will be directed downward down the incline. Okay, so let's calculate for possibility A. The block is on the verge of moving down the incline. So the friction force is directed upward. So here, this is the friction force, yeah, pointing upward. F equals to mu s n, which is 0.2 times n is not known yet. 400 Newton is directed downward. There is a force P here. So if it is 45 degree towards the horizontal, when we know that the slope is 25 degree towards horizontal, it means that this P is 20 degree towards this slope surface. Because usually we choose the XY axis to be according to the slope. And the x-axis is in the direction tangent to the slope. So then sigma fx equals to 0, 0.2 n. This is this friction force, yeah, vertically to inclined. Negative 400 sine 25 degree from where it is. So this is basically from here. Okay, this and this angle is so if this is like this and this is this angle, this is 20 degree. So this is 90 degree and this is also 90 degree. So this angle is also 20 degrees. Okay. So the x component of this 400 Newton, in this case is negative 400 sine 25 degree. Okay. This is this component. And the x component of P is to the right, so it is positive. It is P cosine. And this value is P cosine 20 degree. Okay, so then 0.2 n negative 169 from this 400 sine 25 degree plus 0.94 P. Okay, then from there, x sigma fy equals to 0. N is directed towards the positive y-axis. Negative 400 cosine 25 degree, yeah, from the here. Yes, 425 degree. Then plus P sine 20 degree. Yeah, so yeah, let's draw again. The y component is this one. Okay, so this is P cos negative, yeah, negative, sorry, not P, 400, yeah, cos 25 degree. So this angle is 25 degree. In this part is upward. Yeah, this is P sine 20 degree. So we obtain n negative 400 cosine 25 degree plus 4 P sine 20 degree. Okay, so we obtain n minus 362.5 plus 0.34 P equal to 0. So by equating this two equation, we obtain P equals to 110.7 Newton. Okay, this is, we assume that it's on the verge of moving downward. Yeah, on the verge of moving downward, because here, moving down the incline, it means the friction is directed towards the incline, towards upward. Okay, so possibility B, the motion, the block is about to move upward, so the friction force is going downward. Yeah, remember again, friction force is always opposite to the motion of the object. So sigma fx equals 0, negative 0.2 n. Yeah, from the friction itself, negative because it is now towards the left. Negative 400 sine 25 degree, similar like before, plus P cosine 20 degree. Minus 0.2 n minus 169 plus 0.94 P equals to 0. Sigma Fy equals to 0, n negative upward there, n upward, negative 400 cosine 20 degree, yeah, the vertical downward component of 400 Newton, plus P sine 20 degree upward. So n negative 362.5 plus 0.34 P equals to 0, and P equals to 239.6 Newton. So here we have two values of P. So therefore the range is between 110.7 Newton and 239.6 Newton. Whenever the P is between these two values, the block is in equilibrium. When it is 110.7 Newton or less than this 110.7, the block is on the verge of moving down. The friction is going up. When the P is larger, is equal to 239.6 Newton, it is on the verge of moving up. Yeah, so it means the friction is going down in this case. Okay, so this is category 2 problem. Okay, now category 3. This is related with moment. Okay, tipping or impending motion slipping at some points. To determine whether a block will tilt or slide, observe the dimension of the block given in this type of problem. The dimension, that is, need to use the moment equation. We have to use moment equation. So this is mostly two-dimensional problem. So for example, here a force P is acting on a uniform 80 kilogram block as shown. Determine whether the block remains in equilibrium when P is 100 Newton, B, P is 175 Newton, and C, P is 200 Newton. So mu s is known, 0.2, and the dimension of the block is known, 0.5 times 1 meter. So there are several conditions here. Whether it is slipping. Slipping means when it slides, yeah, the block slides on the surface of that floor. Or tipping. Tipping means it fall, yeah, on the bottom part doesn't move, the upper part move and rotate about the bottom part, bottom surface. So it will tilt. So this is, we are asked to determine whether such object will tilt or slide, which one. So when the P is these values, 100 Newton, 175 Newton, 200 Newton. Now, the first case, when the P equals to 100 Newton. Okay. So here, the weight is how many? The weight is 80 kilogram, right? The weight is 80 kilogram. The mass is 80 kilogram. So the weight is 80 times 9.81 equals to 784.8 Newton. And we assume a uniform density of mass. Yeah, so it is exactly at the middle of this mass pointing downward. Now, there it is being pushed to the left by this 100 Newton force. So the friction force should go to the right. Notice that the friction force F is not equal to mu s times N. So N here, because of this force, yeah, will shift. The N will shift. Why? In order that it still stay in equilibrium. So it's not only translational equilibrium, but also rotationally, they have to be in equilibrium. So notice that there are three unknowns here. This xm, the location of the normal force, the friction force itself, yeah, and the n, the normal is not known. The direction of the normal force n is not to the center of the block. This n will not. Why? Yeah, because of there is this moment caused by the 100 Newton force. Okay, so we have to solve three equilibrium equation. Sigma fx equals 0. So F here, negative 100 plus F, the friction force, equal to 0. So the friction force is equal to 100 Newton with directed to the right. Sigma Fy equal to 0. Normal force, negative 784.8 Newton equals 0. So the normal force equal to the weight, 784.8 Newton. Now, where is that normal force located from the central of the block? So we have to use moment about the point O here. Moment about point O is the middle of the bottom surface. So the normal force N will rotate this block clockwise. So 784.8 Newton times X here, XM, negative 100 Newton times this distance, 1 meter, equals to 0. And so we obtain X equal to 0.1274 meter. Yeah, so this 0.1274 meter is well below this half of the width of the block, which is 0.25 meter. Okay, so since it is within that width, it means it is still in equilibrium and it does not tilt. Yeah. So if X here is above this width, 0.25, tilting will occur. So it will fall from the upper part downward. If X is less than half of this width, okay, sorry. If X is less than half of the width, we check for whether it will slip or not. If the force F is larger than Fm, it means slipping will occur, means it will move. Yeah, move. If this is the floor, it will move translationally. But if F less than Fm, it will still be in equilibrium, it doesn't move translationally. If Xm is larger than half of the width, it will tilt. So there are three possibilities: tilt, slide, or just in station equilibrium. Since X is 0.1274, less than 0.25 meter, the block does not tilt. However, now the Fm equals to mu s times n, 0.2 times the normal force, 784.8 Newton, equals to 156.96 Newton. And the friction force we have calculated from sigma F x here equals to 100 Newton, right? It is well below this F maximum, the maximum static friction force. So then the block is still in equilibrium, it doesn't move still, okay, still in fixed. Okay,
I
so
want to ask,
yes.
can you go back to the moment calculation? Why weight doesn't include in the calculation of moment?
Because this is moment about point O, okay? So point O is here. Remember,
Oh,
so the line of
yeah.
action of the weight is exactly crossing that line. So no distance between the line of action of the weight
Yeah.
towards that point O.
Oh, yeah, okay.
So the contribution of the moment is just from here, from this force, and from the normal force here. Okay, the distance. But no, from weight, no, because it is times zero, right? The distance is zero. Remember the the formula of moment in two dimension. Okay.
Mm.
Okay. So in case A, yeah, this is with where P is equal to 100 Newton. So here we do not have any tipping force or slipping force. So the friction is less than maximum static friction force. That is why it doesn't slip. And the moment also from here, the moment can be is in equilibrium, yeah, equal to zero. So because the xm, the distance here, is still less than the width of the half of the width of the object. Now, what if we increase further the force from 100 Newton into 175 Newton? Let's calculate again. Sigma fx equals to 0. So F, the friction force here, we assume to the right because the pushing force is to the left. So F negative F negative 175 equal to 0. The friction equals to 175 Newton. Sigma Fy equals 0 as well. Normal force is still the same as before, so 784.8 Newton from the weight, from the mass 80 kilogram times the gravity acceleration. Now, the moment about point O, yeah, so from moment due to the normal force, N here, you're pointing from below, times X, yeah, negative 100 clockwise, rotating clockwise, negative 175 times 1 meter here equals to 0. So the xm here obtains 0.223 meter. So from this condition, 0.223 meter is still less than 0.25 meter, half of the block. So it means that the block does not tilt. It is still standing. It does not tilt to the floor. Yeah? So now let's check whether it starts to slip or not, whether it starts to move along the surface of the floor or not. So Fm here is what the friction force is 175 Newton, but now the maximum friction force is Fm equals to mu s times n, 0.2 times the normal force, 784.8. We obtain 156.96 Newton. The force is 175 Newton. So this is well above the 156.96 Newton, the maximum static friction force. Therefore, the block is already in motion. It does not tilt, but it's already moving. So now, since it moved, the motion, the friction force becomes kinetic friction force, not static anymore. Okay, so the actual friction force will be mu k times normal. Yeah, the mu k times normal is I'm not sure if mu k here is given in this problem. No, mu k is not given. So the problem here is just to know whether the block is tipping or slipping or or in equilibrium. Okay, so here we see that When the force is 175 Newton, the block is slipping or the block is in motion, sliding. So solution C. So sigma C here is we increase further the force to be 200 Newton. Sigma Fx equals to 0. The friction now is 200 Newton to the right. Normal force is still the same, 784.8 Newton upward. Now what is Xm now? Sigma moment about 0.0. Yeah, again 0.0 here is the middle of the bottom surface here. So basically along this middle line. So that's why no moment contribution from the weight. Yeah. So from here, then 784.8. This is normal force. Yeah. Clockwise times x negative 200 times 1. So we obtain x now equals to 0.255 meter. So what does it mean then? Since it's already 0.255 meter, already larger than 0.25, the block already tilts, yeah, it falls. So do we need to check for slipping? Of course not. Yeah? So when the block is already fall, so then it doesn't move anymore, right? Except for if we still push the force, then the condition for the width and length already differ from the previous case. Yeah, understood, yeah, for this one. So this is category 3 for tipping and slipping. Now category 4 are problems when involve 2 or more bodies. So for example, here we have a mass B, 40 kilogram, and on top of it, we put a mass A, 20 kilogram, and they are connected through this pulley. Okay, and the mass B is being pulled to the left with a force P. Mu S is 0.4 and mu K is 0.3 for all the contacting surface, or for between B and the floor and between A and B. So now the question, determine the smallest force P to start moving this 40 kilogram mass. A, with cable AB intact, so the cable AB is still intact, and it means it is connected via this pulley. And B, when the AB is removed, so they are just two masses being stacked on top of the other one. So the first case, so there is this slope, there is this rope, yeah, rope or cable AB. So it means then we have pulling force. This is at the upper mass, 20 kilogram mass. There is this mass, 20 kilogram, the weight, yeah, times the gravity acceleration, 9.81 Newton. Then there is normal force from the mass B below it. And there is a pulling force TAB. And there's a friction force. So we assume that the mass A here is being pulled to the right. So we assume that the friction force is directed to the left. Mu S times N1. So equals to 0.4 times N1. And then mu S is 0.4. Sigma Fy equals to 0. Yeah. N1 negative 20 times 9.81 equals to 0. So N1 equals to 196.2 Newton. Sigma Fx equals to 0, TAB to the right, negative the friction force, which is mu S times N1, or 0 times N1. So N1 is substituted from the previous equation, sigma Fy equals to 0, and then we obtain TAB equals to 78.48 Newton. Then we go to the second mass below it, mass B. It is being pulled to the left by the force P, but it is being pulled to the right by the reaction force coming from the cable AB, yeah, TAB. There is this N1, yeah, remember that the normal force, if the mass B is pushing the mass A by N1, so the mass A is also pushing mass B with N1 as well. And the weight of the mass B itself is 40 times the gravity acceleration, 40 kilogram times 9.81 Newton. Since it is moving to the left, yeah, due to this pulling force P, the friction due to the floor will pushing to the right, opposite to the motion of this object, yeah, to the right. Yeah, mu S times N, or 0.4 N, yeah, due to N, the normal force of the total N. But from the upper mass, there will be also friction force. So mass A will exert friction force towards mass B, whose value is mu s times N1. N1 is the normal force between mass A and mass B. Sigma Fy equals to 0. So here the N1 is already calculated previously 196.2. So negative 196.2. Negative the mass of B itself 40. Then times the gravity acceleration times 9.81 plus n is the normal, the total normal force of both masses to the floor. So from here, then we can obtain that normal force 588.6 Newton. Sigma Fx equals to 0. TAB is already known from previous calculation with mass A to be 78.48 Newton. So 78.48 Newton. Negative P here, the pulling force, plus the 0.4 times the N1, the friction between mass A and mass B, plus 0.4 times N. This N1 is already known from previous equation with mass A, and N is also known from sigma Fy, so we just put it there, and then we can obtain P to be 392.4 Newton. Okay, so this is the case when there is pulling and there are cable between the A and B connected through a pulley. Okay, so we are asked to determine the smallest force P when the 40 kilogram mesh starts to move. So we are still working with mu s. Now, when there are no rope, no cable AB, so we are just putting them into one single mass. So both masses will be 40 plus 20 kilogram, 60 kilogram. The weight will be 60 kilogram times 9.81 Newton. So there is a mass, there is a pulling force P. There will be a friction force to the right, mu s times n equals to 0.4 n, and 0.4 is the mu s times the normal force. The normal force is calculated from sigma Fy, which will be equal to 60 times 9.81 or 588.6 Newton. Sigma Fx equals to 0 here, so negative P plus 0.4 n equals to 0. Then we obtain P equals to 235.4 Newton. So here we can compare, when there are ropes or there are cables between mesh A and mesh B connected through pulley, then the friction between the two meshes will also play role, and also the pulling the cable. So here we see that P, it requires larger P, 392.4 Newton, in order to move mesh B. But however, when there are no cables connecting the two meshes, the required P to move mesh B is smaller than previous case, so only 235.4 Newton. So this is problem category 4. Make sure that the friction force is directed against the direction of the motion. So see, this is something that very important, So against F equals to Fm, the maximum static force equals to mu s Newton for all categories except categories 1 and 3. Okay. Analysis for categories 1 and 4 are based on analysis of equilibrium of particle without taking moments. Categories 1 and 4, this is category 4. No need for moments, but when we are doing a category 3 analysis, we need to do it with moment analysis. And all the previous one, category 1 and 2, no need to incorporate moment because we assume that the block is a particle. Okay. So the choice between common or slanting axis depends on simplicity of determining the force component. So slanting here when we have a slope. So when we have a slope here, if we want, we can of course use the usual axis, like this. but it would be simpler because the force are all working in the slope. So it would be simpler as x is and xy axis is directed with according to that slope. Yeah. So rather than the usual conventional one. So it will be simpler if you are using this slope. You can still, of course, use the normal conventional slope, but it will be make calculation more complicated. Now the last category is category 5 when we have a frame or machine problems involving friction. Position of the 8 kilogram block A, this is block A, at the wall is maintained by the member B, C, D. If the coefficient of static friction between block A and surface B, so this is surface B, so means this surface, is mu s equals to 0.25, and between block A and the wall is 0.15. And block A here is on the verge of falling. It is just before it falls downward. So now it can only be in this position because this structure BCD holds it, yeah, because of the friction. It holds that structure to the wall. Determine now the force of the spring and the reactions at B and D for the instant shown. This is more complex, yeah. Maybe in the offshore will come something like this. Complex friction problem with frame and machine. So here at block A, yeah, at the block A, we draw the free body diagram. The end, the first end coming from the floor. Then the second end, we draw it as N1 from the member BCD. Okay. Then the weight itself, 8 kilogram times 9.81 Newton. Then the friction, there are two friction. First is the friction between A and the wall here, which is 0.15 times N, yeah, directed upward. And the friction between BCD member and this block A, which is mu S time, which is 0.25, right? The mu S times N1. N1. Sigma Fx equals 0. So N minus N1 equals 0. So here we obtain N equals to N1. Sigma Fy equals 0, 0.15 N plus 0.25 N1 negative this one, 8 times 981 equals to 0. So from here, since N equals to N1, and we can obtain 0.4 N. This is the same, 0.4 N equals to 8 times 981. So N equals to 196.2 Newton, which is equal also to N1. Okay, so then the question is, so that is the normal force happening at block A. The question is determine the force in the spring C, and the reaction at B and D. So at member BCD, the spring is pulling the member BCD reaction force, yeah, from the spring, pulling it to the left, right? Because it is a spring. Then at B itself, there is the normal force N1. So if it is here at A, it is pushing the A to the left. It means at B, it is pushing to the right. And there is a reaction force, mu Sn. Yeah, here at A, we draw it upward. Here we draw it downward. Yeah, the opposite to the one at A, so that they are, when they are connected, they are in equilibrium. They cancel each other. It's basically it is a two force member. Remember about two force member. Then at C, pulling force spring. That at D we have two reaction forces because it is being here pinned, so it cannot slide horizontally, it cannot slide vertically either. Okay, so there are two reaction forces, dx and dy. Sigma moment d equals to 0, moment about point d equals to 0. So then we don't need to be concerned with dx and dy. And 1 here times the length here is 0.8. Yeah, 0.4 plus 0.4 is 0.8. Negative t here times 0.4 because the spring is at the middle. Negative 0.25 here because it's downward times the length here, which is what is the value? Yeah, 0.15 meter. Yeah, this is times 0.15 equals to 0. So from here we can calculate the value t. T equals to 374 Newton. and the force that the spring exerts to withhold the member BCD. Then sigma fx equal to 0, so dx negative t plus n1 equal to 0. T is already known, n1 is already known from previous calculation. Del dx we obtained to be equal to 177.8 Newton to the right. Sigma fy equals 0, dy upward negative 0.25 and 1. Okay, dy equals to negative 0.25 times the n1 value. Then we obtain the y equals to 49.05 Newton. So we obtain both reaction forces, dx and dy. Then reaction at D is the resultant of dx and dy, right? So D equals to square root of 177.8 Newton square plus 49. Newton square, D equal 184.4 Newton. The theta is arc tangen between dy divided by dx, 15.4 degree. So direction is here. So here, so it is we draw here. So dy, so direction is this one, dy. This theta is 15.4 degree. Reaction at B on member B will be from N1 and this 0.25 N1. Okay, so N1 is 196.6.2 Newton. Okay, 196.2 Newton. N1 here. 0.25 N1 is equals to this one, 49.05. Okay, reaction force at B there. So we obtain 202.2 Newton. The tangen is then, so this is like this. If we extend this way, arc tangen of this times this. So it becomes this. This is the reaction force, and this is 14.04 degree. Okay, so you have to be able later, when you solve such problem, to redraw the reaction force and the direction and the magnitude of that reaction force. Okay. Any question regarding category 5? The difficult part is actually to draw the correct free body diagram. Yeah, often we got confused which should be which. For example, if you are not really trained, a different member, remember on the chapter on frames and machine. So when they are disconnected, so the reaction forces here mu s n1 and the other part should be opposite, the same reaction force but opposite to the reaction force at the other member, the interacting members. Okay, so this will be the last exercise for today. 2 blocks, 10 kilogram mass, MA and MB. So each are 10 kilogram connected by a cable on the incline line as shown. So one is on the 30-degree slope, the other one is 45-degree slope. If the coefficient of static friction between all the contacting surfaces here, mu s as 0.3, determine the mass MB such that mass MA is on the verge of moving up to the 30-degree incline here. First case here. The second case, determine the mass MB if mass MA is on the verge of moving down.